All right, guys, section 9.2, we're going to focus in on the binomial theorem and binomial expansion. And yes, it is as exciting as it sounds. Last year in Algebra 2, you guys would have done at least some of what we're going to be looking at in this. I'm sure you've heard of Pascal's triangle because you did do some binomial expansion in Algebra 2. That's a real common Algebra 2 level topic. So we are starting with that discussion, and then we're going to be kind of building from there. So I wanted to remind you of a couple of things because it would have been a long time since you guys would have seen this. So here's kind of where it all begins. If I were to take a binomial like this, so A represents whatever the first term is, B represents whatever the second term is. If we had A plus B to the 7th power, right, that's what this one is, and I said expand it. Well, to just write it out as A plus B times itself 7 times, and then try to distribute all that would take forever, right? So there were some obvious patterns and shortcuts that got developed for this so that you wouldn't have to do it that way, right? And that's when Pascal's triangle came in, is it laid out a pattern of the terms in the answer so that we could just follow the pattern and model it after that to get our solution rather than really going through the full expansion. So here's why it ties into 9.1. So in 9.1, we learned about combinations. So as you look at A plus B to the 7th, if you really expanded all of that, this is what it would look like. So if you multiplied A plus B times itself 7 times and simplified it, this is what your solution would look like, and that's as simplified as it gets. So what they looked at was the pattern within the coefficients, right? Those are the numbers in front, like the 1, the 7, the 21. So there's a pattern to those coefficients. There's also a pattern to the exponents that hang over the A's and the B's throughout this whole layout. So let me show you something from our textbook here. Actually, I'm going to show you this first. I thought this was a better thing to show you guys. This wasn't in our book, but I brought it up for you guys because I wanted you to be able to see why this works and where Pascal's triangle came from and why it relates to our current chapter. So as we've just learned about combinations, turns out that all those coefficients, the 1, the 7, the 21, the 35, they are all a pattern of combinations. So anytime I have a binomial to the 0 power, this combination would give me the leading coefficient, which is 1. If I had a binomial to the first power, like let's just say A plus B, that's like saying 1A plus 1B, right? That's these 1s right here. Those are my leading coefficients. They both come from combinations. Let me give you one more. So if I did A plus B squared, and we laid that out, the coefficients would be 1, 2, and 1, right? And those 1 and the 1, 2, and 1 come from combinations. And if you look at these, there's a pretty clear pattern, especially if you look at them sort of diagonally. There's a very clear pattern to these combinations that are getting laid out for you for where these coefficients come from. So now let me take you to the book. So if you look at this guy on page 636, so here it lays out up to the 5th power, A plus B to whatever power, right? And so we're seeing here kind of a little more of that puzzle put together. So the first thing that you're seeing on this is just the leading coefficients. So there's a 1. Right here, my leading coefficient is 1 and 1. In the next one, it's 1, 2, 1. Right here, we got the 1, 3, 3, 1. So all those leading coefficients come from these combinations. But you really wouldn't want to do individual combinations to figure out those numbers for every single one. So if I asked you to simplify A plus B to the 7th, you don't want to have to get every one of those leading coefficients by doing an individual combination for each one. That's what this suggests right here, is they're saying, well, you could get each one of those by using this little NCR combination rule that we learned in our last lesson. You could do that 8 times and get all 8 coefficients for that answer. that would be also tedious, right? So this is where the pattern of Pascal's triangle came in, right? If you look at the leading coefficients, let me go back to, I think this one's a better picture. So if you look at these leading coefficients, there's a pattern to these. The initial triangle starts out with a 1, 1, 1 relationship. In fact, there are ones going down the entire left side, and there's ones going down the entire right side, if you want to look at it that way. But what we found is that in each subsequent row, it is a pattern of the numbers above it. So what they did was, if you look at, say, the 1 and the 1, if you add those together, you get the value in between them, which is 2. And so that's why this pattern is 1, 2, 1. As you go down to, say, the next row, we could do the same thing. We always start with a 1, we always end with a 1. All we have to figure out are the numbers in between. So if I do the 1 plus 2, I get 3 right there. And if I do 2 plus 1, I get 3 right there. Right? And we can do that for as many rows as we want to. So let me show you something. And I'm sure you probably did this last year, but I doubt that you remember it from a year ago. So let me quickly go through this with you. We'll just lay out a couple rows of Pascal's triangle here, because I want you to see where those coefficients are coming from. So notice, guys, first of all, this is just a talk about the numbers in front, right? Just the coefficients. We're not yet getting into the A's and the B's. These are just those leading coefficients. They all come from Pascal's triangle. So always starts with that 1, 1, 1 combo. We always put ones on the outside, and then we add these guys to fill in the gap. So if I did 1 plus 1, these would be my leading coefficients if I had a plus b to the second power. If we wanted to do a plus b to the third power, again, I would put ones on the outside, and then I'm going to add the 1 and the 2 to fill in that gap, and then I'm going to add the 2 and the 1 to fill in that gap. And so that would be my leading coefficients for a plus b to the third power. And let me keep going a little bit further. 1 and 1. So if I add the 1 and a 3 together, if I add 3 and 3 together, and if I add 3 and 1 together, so I can fill in the gaps with those numbers. So you could obviously keep going on this as far as you want to. If I went all the way down to a plus b to the 7th, which would be the 8th row, because this is a plus b to the 0, a plus b to the 1st, a plus b to the 2nd, to the 3rd, to the 4th, so on and so on. So if I went down to the 8th row, I would have a plus b to the 7th, and you would see that the numbers I'm laying out are these: the 1, 7, 21, 35, 35, on and on and on. Right? So that's where those numbers come from. So if we wanted to really expand this, that's like the first step in that process, is to use Pascal's triangle to get your leading coefficients. The second step in that process was to figure out the A's and the B's and their exponents. There's a pattern to those too. So if you look at, let me go back to the book's image on this, because this has the A's and the B's in it. So if you look at that, starting with a plus b to the first, every single term has an a and a b in it. But the way that you lay out the exponents would go something like this. If you start with your a terms, they start with your highest exponent. So if this was a plus b to the first, they're going to start with a to the first, and then you count down as you move to the right. So the next one would be a plus, or a to the 0 power. Let me just look at the a terms here. So same thing on this one. So if we did a second power, it's going to be a to the second, a to the first, a to the 0. If it was a third power, you'd have a to the third, a to the second, a to the first, a to the 0. So your a terms, whatever your first term is, it's that to this exponent, and then again you count down as you go to the right. The b's do the same thing, but from right to left. So the b's start with the higher power on the right, and they count down as you move to the left. That's why that one's b to the 0. So go down to this one right here. So if it was a fourth power, we would have b to the fourth, then b to the third, b to the second, b to the first, b to the 0. When you simplify all that, some of it does go away, because obviously b to the 0 is just 1. So anything that has a 0 power hanging on it just becomes a 1, and so you don't really see that entire term laid out the way that you would see it here. So let me take you back to this one. So you can see the way that pattern worked out on this. So this is a to the 7th, a to the 6th, a to the 5th, a to the 4th, counted all the way down to here where they had a to the 0, but again, there's no really point in writing a to the 0 because it's just 1, right? So it's like multiplying this whole term times 1. There's no real point in writing that. Same thing with the b's. They started with b to the 7th, counted down this direction until they got here where they had b to the 0, which went away because for the same reason, right? And so that was the pattern, the way all this gets laid out. If there were other numbers in here, then it would not be quite as simple. This was a very simple problem that they started with because it's only a and b. There's no other values in here. Let's just say instead of a plus b, let's just say this was 2x plus 3, and we wanted to expand that. Well, then everywhere you see an a would get replaced with 2x. Everywhere you see b would get replaced with 3, if that was a 3, right? And then you'd have to simplify all that. So instead of a to the 7th, it would be 2x to the 7th, so you'd be looking at 2 to the 7th times a to the 7th. And then you'd have to simplify all that. So my point is this is a very simplistic view of all that. So as we get to the next part, the idea on this one is, what if I only wanted the information about one of the terms? What if I didn't want to do the full expansion and see the entire thing laid out? What if I only wanted to identify one of those individual terms? A couple things I want you to notice about this. There is an obvious repetition here. As you go from right to left, the coefficients always repeat themselves, right? So you got the 1, 3, and then it repeats 3, 1. Right? It's like it mirrors itself on the other side. So where you see, say, a 4 on the left, it's mirrored by a 4 on the right. Right? So these things get repeated as you go down the line. So like on this one, you see this one as a 7, so is this one. Right? As this one's a 21, then my third term here is a 21. So there's an obvious repetition and pattern to those. Let me scroll down to this guy just a little bit. So if you look at what this one was asking, it just says compute the binomial coefficients. All they wanted was the 1, the 7, the 21, 35, on and on and on. That's it. That's all they were really asking for on this. They just wanted those coefficients. And so they suggested, well, one way you could do that would just be to use combinations, plug in all these different values, and you'll come out with those 8 coefficients. And you could do them that way. You could do it individually, or you could use Pascal's triangle and lay it out this way to find them. So what this one is asking is, again, what if I don't want all of them? What if I only want a specific value within that list? So here's the way they describe it. So let me get you used to their language here just a little bit. If you look at this one, so this is 7, a to the 6th, b to the 1st. The way they would refer to that 7 is they would call it the coefficient of the a to the 6th term. Or they might refer to this one as the coefficient of the a to the 5th term. Or they can use this guy too. So they might say, what is the coefficient of the b to the 2nd term? Right? And we'd say, oh, well, it's 21. So they refer to this by the letter that it's attached to, or at least one of them. So for this one, what they're saying is, what is the coefficient of the x to the 13th term if we were to expand x plus 4 to the 17th power? Right? So obviously this is giant, right? 17th power would be huge. It would even be awful to do it with Pascal's triangle, which is the shortcut version of it. That would take a really long time. So there is a formula that we can use when looking for just individual terms within the expansion, rather than expanding out the entire thing just to find one value. As you look at these, I explain this on the next page, but I'm going to kind of lead you into it with this one. Notice that this initially started as a 7th power. If you look at each term, you'll notice that the exponents always add to 7. This was just a to the 7th and b to the 0. Those add to 7. If you look at the next one, this is a to the 6th, b to the 1st. So 6 plus 1 would add to 7. This is a to the 5th, b to the 2nd. Those guys add to 7. You get the idea. So one of the things to keep in mind for this is that the exponents should always add up to whatever that number is. Right? They call this n. Right? That's going to be the common variable they use for this guy. That's our n term. So this is a plus b to the n power. So these guys should always, each term should always add up to n as far as the exponents go. So if we wanted to identify the coefficient of x to the 13th within that expansion, so here's the setup that they use for this. So they use the combination rather than Pascal's triangle to get this leading coefficient, which is a good move because it would take a long time to expand Pascal's triangle that deep to get a 17th power item. So they're using a combination, which we'll explain. Behind it is your a term and your b term. So here's what I wanted you to notice about these exponents. Notice if that's a 13, because the directions were what's the coefficient of the x to the 13th power. Well, if this is x to the 13th, if that's my a term, my b term would have to be to the 4th power, because 13 plus 4 has to add to 17. The other thing that we get with the combination is this is always my n term, which is this guy. And then this is what they call the r term, which is this guy. So there is some interesting pieces about this. So let me lay out the formula for you so I can give you a little explanation as to kind of how it works. So here's the general layout, right? A plus b to the nth power. Here's the formula that fits that description. Okay, so it's going to be an NCR, which like I just showed on a minute ago. There's two different ways to write this, and this is something I ended up laying out in this explanation because I was confused by this for a while, not this year, but a long time ago. Because in some books I would see it written this way, and in other books I would see it written this way. And I would always be confused as to which way was correct. Well, as I took a little time to investigate it, it turns out that they're both right. It's really the same formula, and here's why. Because remember what we said a second ago. Oops, I wanted to show you this one. Because what we said a second ago is there's a pattern on this, right? So if that's a 4, then that's a 4. So in one formula, you're getting this 4, and in the other formula, you're getting this 4. Well, they're both 4, right? So it doesn't matter which version of the formula we use, they still come out to be the same result. So here's what it looks like, and again, the key is that this exponent plus this exponent always adds to n. And so that's kind of what I went through a little bit on this one. I already talked about how the exponents will always add up to that n value right there. So just like in the one I showed you a minute ago, they always added to 7. So for example 3, the coefficient of x to the 13th looked like this. So if I was first doing that problem, this is where I would have started it. Here's my formula, NCR, and this is my A term and this is my B term. Well, the problem said we want to find the coefficient, that's this guy, of the x to the 13th power, which means I had to put a 13 right there. Well, if he has to be 13, he has to be 4, because they have to add to 17. Right? And so that's how I was able to figure out what this guy was. As far as this piece goes, I kind of lay it out down here, so let me just keep going down on this one before I say too much. So the exponent over the b term had to be a 4, like we just explained. So this was the look that we got right here. Right? So we know that our n value was 17. So I knew this had to be a 17 automatically. This value, and this is where it gets interesting in sort of that math nerdy kind of a way. So remember what we said about the repetition. So this value could actually be him or him. You would get the same answer. If you typed into your calculator 17C13, well, you get the same answer as if you did 17C4. It's the same value. And so that's what I was saying right here. So that's kind of the different ways we can look at that R value that we're seeing on there. So I know that was a lot of explanation. I'm just trying to get some of this to make a little more sense to you guys beyond just the good old-fashioned formula. I wanted you to see a little bit of where that comes from. So let's try a couple together, right? A couple practice problems for us to look at together. So here's some examples of what you guys will be looking at. I'm going to try to close in on that a little. Maybe we can see it a little more clear. So hopefully that helps. So this is x to the 15th, and that says x plus 5 to the 19th power. So what they're saying is find the coefficient of the given term. So if I said, what is the coefficient of the x to the 15th term in the binomial x plus 5 to the 19th power? So we can now easily lay that into our formula. Again, my n value is the 19. Let me just write the formula. So my n is the 19, so I got 19 c something. My a term is the x, and my b term is the 5. And so the way I can lay out the rest of this is going off of this guy. So they wanted the x to the 15th term. So if this needs to be x to the 15th, then what does this need to be based on what we just talked about? Well, remember we said these guys have to add up to n, have to add up to 19, so this must be a 4th power. And as far as the combination goes, really I could use either one of those because 19C15 should get me the same answer. And we can just prove it real quick. So 19C15 is the same value as 19C4. See, so it comes out to be that same value because of that repetition pattern that we already talked about. So I could really put the 15 or the 4 right here to get that value. Anyway, as I look at all this, now I just need to compute the ending value to this, which is, so I'm going to get it one value for the 19C4, which we already know. I also have to multiply that by 5 to the 4th, right? I have to take into account every value beyond x within that setup. So I am going to, let me back out of this a little bit. So I'm going to take that 19C4 times 5 to the 4th and put it all together. So this is that coefficient that they're looking for. All right, let's try it with one more of these guys here. So now they are looking for the term. So this is x to the 10th, y to the 6th, within x plus y to the 16th power. So they're really giving me really more than enough information within this. They want the one that's specifically x to the 10th, y to the 6th. So as I lay this out, again, same formula. My n value is the 16. My a value is the x. My b value is the y. So they specifically said this is x to the 10th, y to the 6th. So they didn't even need to tell me this. I would have known it's a 6 because it has to add to 16. So this one's coming with like extra information here, but that's all good. So this is what we got. So as far as this guy goes, really I could put either the 10 or the 6. It really wouldn't matter. And so for this one, the only value that would matter is this one, right? Because there's no other numbers beyond the x and the y for my a term and my b term. So if I just compute 16C6, that's going to be my winning answer. All right, so let me go down to actually doing one of those binomial expansions that we were talking about at the start of the video. I wanted to do at least one of these with you guys just to give you a reminder of how this works. And I did pick one that was a little more on the complicated side, but I'm sure we can handle it. So I'm going to go, I've already explained a lot of how the layout works for this, so I'm going to kind of dive right on into doing this guy here. So recognize on this one that my A term is 5x, and my B term is negative 3y squared. So first things first, if this is a fourth power, I am considering my Pascal's triangle down to where it would represent a fourth power. So remember, this is for a 0 power. This is a first power. That's a second power, third power, fourth power. And you can also tell what the power is by this diagonal right there. So that's my fourth power. So the first thing I would do on this is I would just lay out those coefficients, 1, 4, 6, 4, 1. I always try to really spread these out. So then I have my A term and my B term are going to go behind each one. So my A term is 5x. And my B term is negative 3y. Right, so there's sort of the full layout. Started with the coefficients, got my A term, my B term. Now all I have to do is fill in the exponents. So remember, if this is a fourth power, starts out with A to the fourth. And then my A terms count down as I go to the right. So this is now A to the third, A to the second, A to the first, A to the 0. And then my B terms, same thing, going the other way. So this is B to the fourth, B to the third, 2, 1, 0. So, realistically, when I'm writing these down, I could leave out my 0 terms. I just am in the habit of always writing those in there so I see the full pattern, especially if I'm doing this in like a lesson example. So there's the layout. So all I have to do now is simplify each term. So I'm just going to start with my first term, which is this one right here. I'm going to start with the numbers. This is 1 times 5 to the fourth times negative 3 to the 0. It's 5 to the fourth. I want to say it's 625, but I could be totally off. It is 625. So I have 1 times 625 times, well, negative 3 to the 0 is just 1. So that's not going to change anything. So this one is just going to be 625. And then now I would throw in the letters. I have x to the fourth, and I don't need to include y to the 0. In my next term, these are all separated by plus signs, by the way. When it's a minus, you will find that your signs alternate signs. So it goes from positive to negative to positive to negative. So it's going to alternate anytime you're dealing with a subtraction case like this one was. If that were a plus sign, these would all be pluses. So I know these ones are going to alternate signs. So on this one, I'm looking at 4 times 5 to the third times negative 3 to the first. So if I multiply all those guys together, so what do we got? 4 times 125 times negative 3. So negative 1,500. And then I fill in my x to the third, y to the first. And I'm just going to keep going and doing that down the line for each one. If you want, you can kind of pause and then check your answer if you want to continue on here on your own. All right, so here it is. when it's all said and done, this is how it should have cleaned up. And that's going to be it for section 2.